All right, I want to do this last part of the lecture on a separate one as opposed to trying to squeeze it in on the previous one. I pulled this slide from your notes, which maybe hopefully you've taken a look at before, but it gets to the idea of how to determine if something is more acidic or less acidic than something else. And if we can kind of see here going through some of the points on here, that's the more polar the acid bond, and or the weaker the bond, the more acidic the compound. So it's like, huh? Let's just look at it this way. Remember we went back to a previous chapter, we were talking about um, the ability to go left and right on the periodic table. That gives you Zeph, right? As you're moving towards the right, you're going to have greater Zeph. And when you move, having a greater pull on electrons from the nucleus, that is going to make the atom potentially more easily to be released. So in these examples up here in this top row, hydrofluoric is the most polar. It's got the highest electronegativity. That is going to pull on that shared pair of electrons more strongly. So therefore, that hydrogen is released relatively easily in comparison to water and NH3, ammonia, and CH4, pretty much not at all. Given this grouping up here at the top, as I move from left to right, hydrofluoric is going to be the most acidic because of Zeph. Now, as you're going down the column, hydrofluoric is actually a weak acid, and that's because of its size. That protons, excuse me, in fluorine are going to be able to have closer proximity to that shared pair, and they're going to hold it fairly tight. But as the radius starts to get larger, increasing going down the column, that hydrogen is going to be more easily released from the pair, if you will. So chlorine is going to pull on those electrons, and hydrogen will be released more easily because it's further away. That proton is further away from the pull of the chlorine. So that's going to be more easily released. So as the size gets larger, the substance becomes more acidic. So we have those two things to play with. And again, you probably want to look at this a little bit and take a look at the arrows and see how this is going to play out for you. Let's go back to our examples. All right, let me focus this in just a little bit. All right, explain the following observations. So we have the answer, we just have to go in and talk about it. Nitric acid is a stronger acid than nitrous acid. And the reasoning for this is as you start putting in more electronegative atoms, that means this shared hydrogen on the compound is going to be more easily released. So again, oxygen is very electronegative. It's going to pull electron density towards itself and the central atom. And it's going to release this rather weak hold of hydrogen in the compound. So we're going to say HNO3 is stronger because of extra electronegative atom on the central atom. Which is nitrogen. So again, it's going to be more easily released. The hydrogen will be more easily released. Let's look at the next one. H2s is a stronger acid than H2O. And based on that chart we were just looking at, sulfur is below oxygen. And as the radius increases, sulfur is lower, it's larger. As the radius becomes larger, the hydrogens are less tightly held. So H2s, stronger. Because radius is larger for sulfur. And I'll just add to that, less pull on hydrogens. Next one, H2SO4 is stronger than H2SO4 HSO4. And the reason for this one is as you start pulling hydrogens away, the remaining hydrogens are held more firmly in place. In other words, when things are somewhat equal in regards to charge, but this one, the resulting remaining hydrogens aren't as free to pull away. Think of it as like magnets. So H2SO4 has lost a hydrogen, therefore remaining hydrogens are more tightly held. For the next one, we're making the comparison. Everything looks exactly the same except for sulfur and selenium. So let's go to one we did up here in B, where selenium is lower, just below sulfur. And because of the difference in electronegativity, it's going to have effect as far as how this actually releases hydrogens. So let me kind of grab a space. I'll do it over here. We'll do sulfur or selenium. It doesn't really matter. Each of them is surrounded by oxygens. And this really helps as far as understanding how it is released. So having an essential atom, whether it's sulfur or selenium, the more electronegative the central atom, the more electrodensity it's going to pull to the center, and the more easily these can be released. So as the electronegativity increases in the central atom, the more easily these guys are going to be lost. So this is a stronger acid because of higher electronegativity on central atom. Okay, the last one on here, we can see right here that the one on the left here, trichloroacetate, maybe, is a stronger acid. Because as we add in chlorines in comparison to having hydrogens, again, these are very electronegative, and they are going to make the connection between this hydrogen and oxygen. It's the same either way, so you may not directly understand that, but having more electronegative atoms in the compound is going to make this connection weaker. So we'll write that in here. As more electronegative atoms are added to the compound, the O to H bond becomes weaker. And that's it. So again, I would probably go back and take a look at the examples in the talk through, either in the PowerPoint presentation I provide or in the book, to get a deeper understanding of this. Because I can tell you this is one of the more, not difficult, but you have to take a look at it a little bit to have it make a little bit more sense.